Good afternoon to all. Myself Mamta Chauhan from Geosciences Division, Indian Institute of Remote Sensing. I welcome you all to the fourth day of DLP course related to hyperspectral and microwave remote sensing techniques for geological studies. As you are all aware that geological studies are not confined to Earth, and we are exploring other planetary bodies also for geological investigation using various approaches and techniques. So I will be talking about compositional analysis of lunar and Martian crust using hyperspectral sensors. In the earlier lectures by our director sir and other colleagues, you have got an idea about hyperspectral remote sensing and spectroscopic analysis of rocks and minerals. So I won't be going into detail about that, but just a brief about the reflectance spectroscopy before starting. Here in this image, you can see reflectance spectra and images of some rocks and minerals. So the view of the top of the planet is only available information to study basic formation process and evolution of the planetary body. So the fraction of incident solar radiation that is scattered back to the space by a planetary surface is a function of wavelength, contain direct information on the mineralogy of the surface soils and rocks. So this unique spectra are like fingerprints for examining these minerals. By collecting spectra from different regions of the planet, the distribution of these minerals can be mapped, and determining their composition for planetary surfaces provide information about origin and geochemical or geological evolution of that region. So they are a sensitive indicator of mineralogy and chemical composition for wide varieties of minerals, and for different planetary bodies where we are getting spectra. So we need a ground reference samples. As in case of lunar minerals, we have Apollo and Luna samples as well as meteorite samples. And for Mars also we have got meteorite samples. So ground reference samples are very helpful for interpreting remotely measured spectra. Now coming to the various hyperspectral sensors on board Moon and Mars mission from Indian and various Indian and various other international agencies. So these are the important hyperspectral sensors. This is the hyperspectral imager on board Chandrayaan-1, at having spectral range of 420 to 960 nanometer with 64 spectral bands with a spatial resolution of 80 meter. Then Moon Mineralogy Mapper having spectral range of 430 to 3000 nanometer with the channels of about 85 and spatial resolution of 140 meter. Spectrometer infrared from Munich, CER2. It was also on board Chandrayaan-1, having spectral range of 940 to 2400 nanometer, and number of bands were 256 with a spatial resolution of 220 meter. Then spectral profiler on board Kaguya Selene mission. It was JAXA's mission. It has spectral range of 500 to 2600 nanometer with 296 bands and spatial resolution of 500 meter. Then our recently launched Chandrayaan-2 imaging infrared spectrometer, and having spectral range from 716 to 5000 nanometer, and with number of bands being 256 and spatial resolution of 80 meter. And these are some of the Martian spectrometer, hyperspectral spectrometers that are present on board various Martian mission, Martian Global Surveyor, thermal emission spectrometer having range from 5800 to 50,000 nanometer, and 137 bands and spatial resolution of 0.3 to 4 kilometer. Omega on board Mars Express with 380 to 5100 nanometer with through 352 bands and 350 meter spatial resolution, and CRISM compact resonance imaging spectrometer on board Mars Resonance Orbiter having spectral range 400 to 4000 nanometer and 554 bands, and with spatial resolution of 15 to 38 meter. So this development of this hyperspectral remote sensors and imaging spectrometer, it is now possible to detect and quantify the compositional variation on planetary surface. In context of planetary geology, these sensors are very useful for accurate identification of mineralogy from these regions of interest. Now coming to the, let me brief about the mineralogy of Moon and Mars. And this image, you can see the image of near side of the moon. Here you can see dark region, and that is the mare region, that is mainly basaltic region, and this is the bright highland region. This mare basaltic region is comprising nearly about 17% of the lunar surface. Rest 83% is on the near side as well as on the far side, that comprises about 83% of the lunar surface. And these are example of some of the rocks that are present on the moon, that were samples were available from Luna and sample missions, and these are the landing sites for Apollo and Luna missions, from where return samples have been acquired. So the surface of the moon is covered by fragmented and unconsolidated material that we termed as regolith, and due to lack of atmosphere and therefore any weathering agents, the lunar surface composition is less varied when when compared with the Earth. The geochemical analysis of these return samples reveals that there are mainly 4 major types of rocks present on the moon. And the number 1 is a bright colored pristine highland rocks. These bright highland regions, these are characterized by presence of anorthosite. We termed as highland rocks that form the primary crust of the moons, and these are formed directly by cooling and crystallization of initial phases of during initial phases of the formation of the moon, and therefore represent primary crust, and their mainly composition is anorthosite along with norite, gabbro, and dunite and troctolite. Then the second lithology is basaltic lithology. They are volcanic rocks that form these low albedo dark circular regions. They are present in form of lava flows, pyroclastic deposits, and generated by partial melting of the lunar mantle, and they are rich in iron and magnesium when compared with the highland rocks. Then the third category is brick-sheeted rocks. These are formed by impact processes. As you can see on the surface of the moon, various circular depressions have been formed, and even also these large depressions, these are formed by impact cratering. So impact cratering has not only resulted in generation of these depressional features, but also has resulted in crushing and melting of the the primary crust of the rock. And therefore the brick-sheeted material has formed, mainly consists of the material generated by crushing and of these rocks and melting of this pristine lunar rocks during that hypervelocity impact. They can be monomictic and polymictic depending upon whether they are composed of uniform lithology or whether they are mixed nature. Then the 4 important lithology is lunar regolith. We can say lunar soil, which covers the entire lunar surface, and that is very fine, powdery, fragmented, and unconsolidated material formed due to mechanical disintegration by repetitive impact events and continuous bombardment even by small charged solar wind and interstellar particles over millions of years. And they are mainly composed of fine rock fragment, glasses, agglomerates, brick-sheeted fragments, and their composition ranges generally from anorthositic to basaltic, and the grain size may vary, and it is very fine grain. So these are the important rocks, and these are the important minerals, the main minerals being plagioclase, pyroxene, and olivine, and accessory being oxides, ilmenite, chromite, perovskite, spinel, rutile, zircon bearing, zircon, bedellite, quartz, tridymite, that has been recorded from the return samples from the return mission Apollo and Luna samples. These are the reflectance spectra of these lunar minerals. They are in VNIR region. They are characterized by various absorption bend center which are diagnostic of that particular mineral. For example, if we see magnesium spinel, it is characterized by broad absorption at around 2000 nanometer. Similarly, for chromite also, there is a 2000 nanometer absorption feature, but that is slightly longer. That is for magnesium spinel, it is 2.1, it is 2.2. Then olivine characterized by broad absorption feature around 1000 nanometer. Then this is the brick-sheeted material, it is more or less featureless. This is soil spectra. Then these are the spectra, this blue one is spectra of plagioclase characterized by 1.25 nanometer absorption feature. And these are the pyroxenes, this yellow one and red one. These are the pyroxenes, high calcium and low calcium pyroxene characterized by presence of 2 absorption feature, one near 1000 nanometer and another 2000 nanometer, and the difference being longer or shortward depending upon the presence of calcium and iron, magnesium. So with increase in calcium, the wavelength shifts towards the longer side. And this is again the spectra olivine. Now, when coming to the Martian mineralogy, much of the Martian surface is covered again by unconsolidated soils that is derived from the variety of impact. And because of presence of atmosphere on the Mars, there are other various processes going on the Mars due to aeolian and other sedimentary process. So it is characterized by distinctive reddish hue, and that is imparted because of the presence of iron oxides, ferric oxides, and oxyhydroxides. So the Martian regolith, which is showing reddish in color. So while on the moon we are observing only primary minerals, Mars has also secondary minerals that are formed by alteration of the minerals by water. So the minerals are categorized into primary and secondaries. Primary minerals, which are the most abundant minerals, and they are mainly of basaltic or andesitic composition and characterized by the mineral olivine, orthopyroxene, clinopyroxene, plagioclase feldspar, and also evolved lithology in form of alkali feldspar has been detected in the Mars. Other than silicates, sulfides, and oxides has also been detected. And these are the secondary minerals that has been formed by alteration of these primary minerals in form of oxides, hematite, goethite, ekagonite, then clay minerals, phyllosilicate in form of smectites, serpentines, hydrated silicates, carbonates, sulfates, chlorides, and perchlorides. Now I will be discussing about the various results that have been that we have found after the analysis of results from hyperspectral sensors, recent hyperspectral sensors, mainly from our own mission Chandrayaan-1 and Chandrayaan-2, and also I will be discussing about the water mineralogy present on the moon and as well as Mars. Now coming to the important minerals. After the arrival of that is after the M-Cube sensor, moon mineralogy mapper on board Chandrayaan-1 was flown on board Chandrayaan-1. Many new minerals, after acquiring that data and after that analysis, very new minerals have been identified, and magnesium spinel is one of them. And magnesium spinel is unusual in the sense because it was also earlier also reported from the sample lunar samples, but it was associated with the mafic minerals. For the first time, magnesium spinel was found associated without any mafics, and that's why it was an unusual mineralogy that was first time detected through the orbital measurements. And it has been reported from various complex craters. This is examples of crater Theophilus, from where a spinel was detected. It is characterized by a broad absorption feature at around 2000 nanometer. And these are the color composite images from the M-Cube data. And these are the spectra and from acquired from various other, this is for Theophilus, this is for Thomson craters. And these are the associated mineralogy that were present along with this magnesium spinel. Spinel have been detected from various other tectonic settings also, besides the central peaks. They have been detected from the basins of the craters. And here another crater Tycho, where from the central peak of the crater magnesium spinel was detected. Then from Lowell crater, then this is Mare Igni from the Thomson crater, then Latroni basins, then rugged highland features within the Mare Imbrium region. These are near to the plateau crater, Mons Pico and Mons Tenerife. There are various regions from where this unique spinel lithology has been detected through the orbital measurements. Then besides the central peak and association with the anorthosites and other mafic minerals, spinels have been also found associated with the silicic volcanic lithology, which is again an unusual occurrences, and it has been detected at some of the red spots, that the silicic bearing lithology that we termed as a red spot because of their relatively high albedo and strong absorption in ultraviolet region, and they are characterized by large percentage of silica. So they are mainly of rhyolitic or dacitic aphanitic. This is one of the region Henstein alpha where spinel has been detected. And this is another one volcanic complex, Compton-Bilkovich volcanic complex, comprises of various volcanoes. And here also spinel was detected. This is the spinel spectra acquired from the Compton-Bilkovich volcanic complex. Then other than magnesium spinel, chromium spinel has also been identified, and this has been associated with a dark haloid crater, that is pyroclastic deposits at various regions. And this is the region sinus ostium, from where this is a color composite image of sinus ostium, and this is this spectra of chromium spinel, and that is characterized by somewhat longward absorption band near to about 2.2 and with an additional absorption band near 700 to 750 nanometer and at around 900 to 600 to 900 nanometer absorption feature. So this is the chromite spectra that is found associated with the pyroclastic deposits of the sinus ostium regions. This was also an unusual discovery from the M-Cube data. This is the global occurrences of spinel that has been detected from various tectonic settings, including the basins, their central peaks, and their whether they are associated with the silicic lithology or whether they are associated with the dark mantle deposits. This is the global distribution of the spinel that has been marked on that LOLA data, elevation data, and these are the blue color indicates the lowest elevation and red color indicates the highest elevation region. So the spinels are mainly associated with the lower crustal regions, and these are the spinel spectra acquired from the various different regions. Then high resolution compositional data from moon mineralogy mapper has also revealed an unusual lithology dominated by high concentration of olivine, orthopyroxene and magnesium rich spinel that is designated as OOS lithology and has been detected from Moscovici basin and Endymion craters. And this such type of lithology and tectonic setting hints towards deep seated origin, and it is very helpful in understanding deep crustal composition of the moon. And these are the various color composite images and the location of the spinel that have been detected from Moscovici craters and Endymion crater. And this is another location, Sinus Iridium, where this type of lithology has been reported. So identification of plagioclase is also important contribution by moon mineralogy mapper, because earlier instruments have identified areas that were consistent with an orthosite based mainly on the spectra that exhibited the various characteristic of plagioclase dominated rock, mainly in form of high albedo region, lack of mafic mineral absorption, a low model percentage of olivine and pyroxene. But the clear indication from spectral analysis was not available. So that M-Cube spectra having spectral coverage from 0.23 micrometer, and it was very useful in identifying the absorption of plagioclase characterized by absorption band at around 1.5 nanometer, and was easily able to demarcate the pinpoint the plagioclase dominant lithology. This is the crystalline plagioclase characterized by these absorption features, and because of the shock induced by impact crater, this 1.25 micrometer features is lost and it showed featureless spectra. So this is the spectra of plagioclase, and these are the regions where plagioclase has been identified. The importance of this plagioclase is because in plagioclase form the primary crust of the moon that has been formed during its initial formation, during its initial crystallization process that has resulted in flotation of the plagioclase crystal that has formed its upper crust. So that is a part of primary crust. This is M-Cube data that have globally assessed the occurrence of pure crystalline plages across the moons by its diagnostic plagioclase absorption feature. And these are the red colors that are indicating of the pure crystalline plagioclase that has been identified from M-cube spectra. And this is the global image of LOLA data, Lunar Orbital Laser Altimeter Topography, overlain of Lunar Reconnaissance Orbiter, wide-angle camera, albedo global mosaic image. Besides M-cube data from Chandrayaan-1 data, basalt mineral has been the data was also utilized for characterization. Means besides the various identification of important minerals, it was also utilized for characterization of basalt mineralogy, based on the identification of the mineral recognized by the spectral features in VNIR regions. Apollo and Luna missions have sampled a subset of moon basalts that have erupted during the 4.3 to around 3 billion years ago. So they have characterized the basalts on the basis of low titanium and iron content, and they have classified them into high titanium, low titanium, and intermediate titanium, medium titanium basalts, based on the analysis, geochemical analysis obtained from the Luna and Apollo mission samples. And also earlier telescopic studies and multispectral data also Clementine was utilized for mapping basalt based on the number of spectral types based on continuum slope, albedo, near infrared absorption features of mature mare soils. Hyperspectral data from M-cube enabled classification and characterized of lithological variability of basalt based on the spectral parameter acquired from the pyroxene geochemistry, and help in identifying various lithology based on mineral variability, and that has also been utilized to determine various petrological parameters including the formation, temperature, depth of origins. So these are the various examples where M-cube data has been utilized for characterization of the basalt. This is the region of Mare Oceanus Procelum, and this is again the subset of this particular region where different basalts has been identified based on their mineral variability. This is color composite image. And this again, the Mare Serentitis area, whereas the different litho units has been classified on the basis of their pyroxene variability. This is the spectra of the pyroxenes taken from different parts of this particular crater, and has been identified, has been utilized for understanding the variability present within this crater. And this is again where the spectral parameter were utilized for generation of the determination of the temperature as well as compositional variability. So besides M-cube, other sensor Hi-C and SIR was also determined for compositional mapping using various spectral band parameters. Because of the limited range of this Hi-C data, then again this spectra were used based on the various spectral band parameters were used for compositional mapping for the pyroxene variability based on the spectral curve and other various parameters. And this is example of the analysis that done using this SIR-2 instruments that have utilized comparative normalization analysis technique to emphasize spectral features and track the various absorption variation and for various mineralogy, and then they have utilized various determine to track the variability of the minerals present across this Aristoteles crater. Then starting with the this water on Moon and Mars. Water, as we know, that plays a very crucial role in planetary evolution. It is spectroscopically, it is identified by its absorption at near about 1.4 to 1.5, then another at 1.9, and at around 2.7 to 2.9, and when we go further, it is around 6 nanometer. So water existed on the Mars as well as water has been detected on the Moon, but the stories are different. Coming to the Mars, water existed on the Mars, and water was present in the liquid form earlier in the Mars during its period from 4.1 to around 3 billion years ago, that we termed as a Noachian and early Hesperian eras. During that time, atmospheric pressure on the Mars was higher than it is today because of the atmosphere contained large amount of carbon dioxide, nitrogen, as well as water vapor. So these gases were more effective in warming the atmosphere, and the resulting climate of the Mars was warmer and more humid than it is present. But now at present there is no evidences of large bodies of liquid water anywhere in the Mars. But there are a lot of evidences of frozen water ice from polar caps, and that is stable in the subsurface conditions. So direct evidence of water from Mars comes from several sources. They include telescopic observation of near-infrared water absorption, measurement of water content, also by Viking lander gas chromatograph mass spectrometer, then Viking mass atmospheric water detection that detected water from in its atmosphere. Then observation of 3 micrometer absorption feature indicating water from the Mariner 6 infrared instrument. Then Phobos 2 imaging spectrometer for the Mars. Then water proton abundances was measured by Mars Odysseus GRS instrument. The dark the blue color region indicates the area which are high in protons. Then another thermal emission spectrometer observations also indicated presence of 6 micrometer absorption indicating of water. Then presence of other hydrated minerals has been detected from the Martian meteoroids, which we termed as SNC meteoroids. This is an example of the water from that is phyllosilicates that has been detected using CRISM data. These hydrated minerals are from the region near around the zero craters has been identified from prism observation. This is color composite in image. That is the red and magenta color indicates the area where there is high absorption. There is content of these smectite and carbonates. And this is the high resolution image taken from the high rise image indicating the mode of occurrences of these water containing or hydrated minerals that are seen to be present in form of layer deposits. Now coming to the moon, when compared to the Earth, the bulk moon is significantly depleted in volatiles. While small amount of water was reported in the lunar soils returned from Apollo missions, they were generally attributed to terrestrial contamination. So consequently, in post-Apollo era, there was a consensus that moon was primarily an anhydrous planetary body that contained less than 1 ppb of water. Regarding the sources of water on the moon, water could be divided into endogenic or exogenic. Endogenic, we say when it is present within the moon, and since its formation, so it is derived from its interior sources. Now it is coming out with the volcanism or pyroclast form. Exogenic, the water that has been added to moon after its formation from various multiple sources, either be comets, meteoroids, or asteroids, or from the solar winds induced proton implantation. So these cometary water, that water contributed by comets, asteroids, and meteoroids, that we term as exogenic water, that is most likely to be present in the polar regions. And other water that is found by the solar wind hydration, that is uniformly present in more or less most of the regions, and it is continuously produced by reduction of lunar oxides by solar wind protons, the high energy solar wind protons. A variety of observations and measurements over the past decade have presented new evidences of water, and all the 3 types of water has been reported from this. 3 means one endogenic and 2 exogenic. Exogenic cometary region and another solar wind induced. So all these 3 types of water has been found on the lunar surface that has confined to various confirmed by various satellite missions. This is an example of orbiting spacecraft Lunar Prospector that was launched in 1998. These are results from the lunar prospective spectrometer that has sensed a large amount of hydrogen in the lunar poles. The instrument, a neutron spectrometer, has detected water from the polar region by measuring the abundances of hydrogen implanted by solar wind, which was theorized to be in form of water ice. Then another LCROS instrument, Lunar Crater Observation and Sensing Satellite, it was a robotic spacecraft operated by NASA that impacted the permanently shadowed crater Cabus near the moon's south pole, and the resulting ejecta was analyzed for volatiles and found to be the presence of various volatiles, including water, carbon dioxide, methane, then H2S was also detected along with OH. Then MIP, Moon Impact Probe, developed by Indian Space Research Organization. The probe separated from Chandrayaan-1 on 2008, 14th November, and it crashed and struck the Shackleton crater. And then again, and its analysis show presence of volatiles and presence of water and ice. Then Deep Impact Epoxy, NASA's extended mission to Deep Impact spacecraft, is targeted to flights by comet. So in 2010 November, so en route the comet, the spacecraft has numerous close observation of Earth moon system and has observed the moon, and particularly this water absorption features in the near infrared spectrometer. Then another Cassini mapped the distribution of water using the data from VIMS, visual and infrared mapping instruments, and it has shown the water and hydroxyl absorption in many of the locations on the lunar disk. Now these are the results from Chandrayaan-1 MQ Moon Mineralogy Mapper. That was a near infrared imaging spectrometer. There's already briefed in the earlier slide. It detected a broadly distributed OH signature present across the lunar surface, with abundance increasing towards the moon. So these blue regions indicate the presence of high presence of water pertain to the polar regions. This is the spectra of water taken from MCube data. And then global map of OH relative band depth index was also generated. And the strongest absorption again show features that are more confined to the polar regions. And the lithological preferences were also reported and were analyzed from the north. And this is one of the region of the northern polar region. And the water absorption was analyzed for its preferences of the mineralogy, and it was consistent that, with the laboratory study that showed that plagioclase mineral can absorb as twice as water or OH or H2O as basalts and glasses. So this is lithology, plagioclase lithology. It is in Goldsmith crater where water absorption was found to be strong. Then water was also detected using the radar data, synthetic aperture radar from MiniSAR, and it was also utilized circular polarization ratio that depends upon the dielectric constant of the scattering material, and therefore its CPR value was used to distinguish water from the soil and can be used as an indicator of water ice. So it has also indicated presence of water in the polar regions and tried to segregate the craters which are having water absorption or water ice indications, and then those from the fresh crater without it. Then besides these exogenic water, endogenic water has been detected through MQ from various lithology and from various regions. This is Buladilus crater, whose central peak is of noritic composition, from where water was reported. Along with this is the norite spectra consisting of orthopyroxene, and this is the water absorption. Then the strongest absorption of water was detected from CBVC, Compton-Belkovich volcanic complex, from the far side of the moon. It is a silicic lithology, and it was characterized by a strong absorption of water. here you can see it is around 2.8 micrometer, ranging from 2.8 to 3 micrometer. Then at Jackson crater in the central peak, water was detected along with plagioclase. Then at Theophilus central peak, water was detected along with different lithologies. Then again, these are silicic lithologies, Crustacean dome and Hansteen alpha, from where water was detected. And these are all relates to endogenic water, the water associated with the magmatism, and that means have been generated present in the lunar interior and has been exposed or through the volcanic magmatic processes, either associated with the particular lithology, whether it is silicic or whether it is noritic or anorthositic. Then coming to the infrared imaging infrared spectrometer, which is a new sensor from recently launched orbital payload Chandrayaan-2. It is an advanced version of hyperspectral imaging sensor on board Chandrayaan-1, whether it is M-Cube Hi-C, and it has spectral range from 800 to 5000 nanometer, and it is mainly designated for mineral mapping. Having surface number of bands are 256, and with a ground resolution of 80 meter and swath coverage of 20 kilometer. This is the table showing specification of IIRS sensor. This sensor measures both reflected and emitted radiations. That is the radiance. This image shows the radiance distribution of the IIRS spectra from 800 to 5000 nanometer with reflected and thermal component. And this is the image cube generated from IIRS spectrum. This is an image, and this data has been utilized for identifying various minerals that are present on the moon. And these are the spectra generated for various minerals, and this instrument was very helpful in unambiguously detecting and quantifying water on the moon. These are some of the initial results that has been published from utilizing the data of IIRS reflectance data. They have showed unambiguous detection of lunar water absorption feature that is present in this range 2.8 through 3.1. Whereas in M-Cube, it was only confined to 2.8, and due to thermal contribution, it was not easily, we are not able to assess the see the complete picture of this absorption feature. Now with the IIRS, the complete picture is clearly visible. And then these three strips were initially analyzed, and they have been utilized not only to detect the water, but also to quantify the water and the study variation of hydration absorption feature and its dependency associated with the different latitudes, surface temperature, and lithology. So for details, you can go through this paper. So this was all about the various minerals detected from the recent lunar and Martian missions, mainly from the Indian missions, and that has been the results that has been generated from the analysis of hyperspectral sensors on board Moon and Martian missions, and also the important mineralogy that is present over the Moon and Mars. So how the hyperspectral data have contributed to identifying the various minerals and also in detection of the new minerals from the using the capability of hyperspectral sensors. So this is all about compositional analysis